Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to very quickly introduce as many Alex speakers as we could find on our topic of natural language interaction. So this is the full total of Alex. No, there's many more. But Professor Alex Rednicki and also Rednicki and Alex Cicero will now tell you about natural language and how that fits into our thinking about natural user interface. Thank you.
Good afternoon. You can hear me, right? So in this session, I'm going to give you an update of some of the work we've been doing on natural user interfaces by using speech. You've been hearing a lot about direct manipulation, touch, and pen, and other gestures. And today, we'll see how speech can fit in here. So yesterday in the keynote, you heard about Kinect. And you saw a demo where there was not just a way of pushing this to flip the slides, but also to interact with speech with the device. So let's see how both can be complementary. This is a brief summary of what the gesture recognition can do and the kind of interfaces that you can build with it. You can move your hand and scroll around. But it also has voice control. This is one of the features that is shown in this video about the voice control in Kinect, but there are more. So no need to fumble in the dark to find your remote control to pause or to fast forward. So what is the role of speech recognition in Kinect? And I'll start trying to tie the speech functionality into Kinect and then explore some other scenarios where speech technology can be useful for natural interfaces. So first of all, we feel that speech is complementary to gestures. There are some things that are better done with gestures, like if you want to flip to the next DVD, that's a very natural thing to do. But in other cases, if you want to talk to your animal, and you saw a demo of that Kinectimals game yesterday, jump. Hey, come here, jump. Well, you just want to speak because that's just the natural thing to do. Sometimes when you want to do voice control without on-screen buttons, for example, in the case of Xbox Stop, well, there are no buttons because you're just watching the movie full screen. But it's important if you can just do some interfaces that way, or if you have access to long lists where scrolling or just the direct manipulation could be cumbersome. Those are places where speech recognition could be useful. But one of the many problems that we faced when working on this project is that we don't have headsets. The speech recognition has to work at 10 feet away, 3 meters typically, and that's very challenging. First of all, because there are loud gaming sounds, explosions, and whatever coming out of your 5.1 surround system, and there is noise and reverberation in the room. So this is a rough outline of what we'll be talking about today. I'll start with the audio processing work we've done, describe some voice search, voice control in a robust way, voice interfaces for the automobile, going to voice dialogues, error correction, and other speech interfaces. So the topic is more like how can we use speech to build interfaces as opposed to tell you everything about how inside the engine works. I will cover nothing about that part today. So this is what the audio stack for the Kinect device looks like. And we have over there a microphone array that you can see, followed by a multi-channel echo canceller, followed by a microphone array, acoustic echo suppression, and noise suppression. And that has to cancel the speech, the music, or the sounds that the games are putting out through the loudspeaker. And on the other side, we have to use this stack both for voice chat, which is one of the features of the Kinect device, as well as for voice recognition. So let's talk first about the audio stack. The first thing that we did is Ivan Tashev, one of the members of the group, helped design the microphones. And this is a little bit of a black art because The way you put the rubber boot there makes a big difference on what the directionality of the microphone is. Yet it's very important. You see that's the directionality pattern of the microphone in the Kinect device, which the more directional it is, the more likely it will pick sound from in front as opposed from the side or the fan or like the receiver that is just underneath. The other thing that you notice is that the geometry of the microphone array is a little bit unusual in that it's not symmetric. A lot of the microphone arrays that you see are symmetric. This is not symmetric because it had to be this size. And by using this, we can use the minimum number of microphones that cover the maximum range of frequency. So the next problem you need to do is echo cancellation. If you're killing some of your enemies and there are explosions everywhere and there are characters talking, if you don't do anything, and the recognizer is listening, it's trying to recognize that, and it's not going to work very well. So this is just the traditional acoustic echo cancellation where you have the signal coming out of the speaker that is picked up by the microphone, and you want to estimate a filter such that you cancel that away. And that's a well-known problem that has been studied for many years. One of the problems in real life is that there are non-linearities. This is the real and the ideal world, but there are non-linearities in the microphone, in the speaker, in the room, in the A to D converters, and so on. Plus, things are changing over time, which make even this, in practice, not an easy problem. But it's even worse once we're talking about not just mono, but multi-channel echo cancellation. And that's precisely the problem that we have at hand. We are playing 5.1 sound through the speakers, and we need to cancel it. And we know that this presents a fundamental limitation because of the non-uniqueness. This is something that has been well known for a number of years. We are trying to estimate these two filters at the same time. There are just too many combinations that are possible, and it's not a well-determined problem under those conditions. So what Ivan proposed a couple of years ago is how about if we calibrate a couple of fixed filters, HL and HR, and then have just a single adaptive filter and estimate that alone. That's not a perfect solution, but it's an approximation that works reasonably well. So what the system does is place a calibration sound. And with that, it's able to adjust those two filters and initialize the adaptive filter. And you'll see that it does a good reduction in echo, and the entire pipeline can do even up to 35 dB. So the next step is to do beamforming. So we have 4 microphones, and there are people sitting maybe in the couch, playing a game show or watching TV. And what you want to know is distinguish who the speaker that is talking to the device is versus the cat or the kid playing in the corner or some other noises, the dishwasher running in the kitchen. So to do that, you want to be able to create a beam that points to the person that is talking, and that's what this adaptive beamformer does. You see up there the frequency spectrum as a function of the angle, and in that case, you see that it put a null at 5 degrees, and maybe aimed at a higher, 10 degrees or something like that. Another thing that we do also is spatial filtering, which is looking at the sound that is coming on a particular direction and trying to suppress all the frequencies in that direction. And overall, we can get a few more dB of attenuation that way. And finally, traditionally, when people build these acoustic components, it's done individually, separately. But one of the things that is well known from the other speech recognition communities is joint optimization. So what Ivan did here is try to optimize the parameters of all of these components, the multi-channel echo canceller, the noise suppressor, the beamformer, the spatial filter, the noise suppressor, all of those components to increase PESC, which is the perceptual evaluation of sound quality. So all of them tweaked in an optimization until we found the optimal solution. And when evaluated this on a speech recognition system, what we see is the black curve is if you don't do anything. This shows loudspeaker volume and word error rate. So if you don't do anything, the word error rate creeps up quite quickly because you cannot, it's trying to recognize the output of the speakers. Once you run this system, but before optimization, it improves quite a bit, especially when it's relatively quiet. But because the echo canceller just cannot cancel everything, maybe that's a misnomer. It should not be echo canceller. It should be echo attenuation. Because of the non-ideal conditions, it still does quite a bit leaks for higher volumes. After optimization, it gets better. And after we retrain the recognizer so that it's learn what the echo cancel signal looks like, then we get even better, and we believe that that could be acceptable for traditional volumes and places where we can have an error rate that is low enough that we can build a sufficiently good speech interface. So that's an outline of some of the work that we did for the Kinect device. Now let me go to the other side of the spectrum. We talked about the audio capture. Now let's talk about the interface. How do you build interfaces that use speech? So one of the things that we build is a voice search interface for frequently asked questions. So this is what the system feels like.
Is Project Natal the next version of Xbox 720? Will the game Halo work with Project Natal? Do I still need the controller once I have Natal? I want to learn more about Project Natal. When can I buy Project Natal? What is the expected price for Natal? Which game will support Project Natal? Which one is better, Nintendo Wii, Xbox Natal, or Sony's motion controller?
So this is an example of a possible application that you could have on your Xbox device, where you're asking questions, and rather than flipping through a manual, just ask the question. How did we do that? Well, we did a traditional voice search architecture, which is you have a library of all the text that you want to be able to recognize. In the previous case, it was the whole manual. But I'm going to show you here an example where we use this for business search. And there are several applications on the market where you can just speak the name of the business on your mobile phone. The voice is sent through the data channel to a server, gets the recognition, gets back. So how does that work? So in this case, you say, pick the yellow pages and get Pizza Hut, Starbucks, millions of entries like that. And we build what we call an SLM, statistical language model, which is essentially counts of how many times the word pizza happens in that data, as well as that's the unigram, as well as bigrams. How many times the word hot occurs whenever we saw the word pizza as opposed to some other word. Those are the bigrams and trigrams. And that's what typically a lot of speech recognition systems use. At the same time, we build an index similar to what we do when you do a search engine. Basically the same. And use techniques such as TF-IDF or BM25 or other more sophisticated techniques. So when someone speaks, the first thing that we do is we recognize with a generic language model. Let's say maybe we say Starbucks. And then we search, just like if you had typed that word in your search engine, and you'll find that the entrance is Starbucks coffee. Maybe the apostrophe is not right. Maybe it doesn't have coffee, but search engines can deal with that too. So this is one case where we can use this for a voice search application.
What city and state, please?
Seattle, Washington.
That's Seattle, Washington, right?
Yes.
What is the listing?
Microsoft Corporation.
Microsoft Corporation. Is that correct?
Yes.
I found one on Microsoft Way number 8.
Redmond, the phone number is?
Area code 425-882-8080.
Thank you.
So this is an example of a business search and directory assistant style application. And we use the same for the frequently asked questions. One of the things that we do here is use live data to improve the system. So we have initially the phone book where we use to build the language model. We have some acoustic models, basically hidden Markov models with Gaussians. and we put everything to a big rack of servers in our data center. Someone calls, and we show the alternates in the screen. And the thing that we do later is we capture what the user clicked, and we use it to improve the acoustic model and also the language model. So now I gave you a quick overview about the techniques that we use for voice search, which are fairly standard in the industry. So now let me tell you about how we can use that for robust voice control. If you're building voice control applications, traditionally what people in the industry do when you call one of these 800 numbers and you get a machine to talk to you is to use a context-free grammar, which looks like that. You need to write an XML format that describes all the options that the recognizer is listening for. So it can listen to either business search, biz search, driving directions, you name it. So you just enumerate all of them, and that's what the recognizer is listening to. And that works quite well if the user says one of those things exactly. But let me play you. This is a live system that our subsidiary TellMe deployed. Let me play you some of the recordings that people actually say, because they don't get to know what the menu that we use is.
Turn-by-turn directions. Business search.
Business search.
So unfortunately, those CFGs are easy to write. Most developers without speech experience can do it. They know what the options are. But users don't follow that. They say business search. Well, it doesn't match any of those. It's only if you say business search, not if you say business search. Or if you say directions. Well, the system is going to struggle and the error rate just plummets. But that's just what people say. So what do we do? So we build a similar mechanism to what we did for voice search. But in this case, we used it for a voice control, traditional command and control application. So what we ask is that you provide an example of the developer of what you think the user would say directions, and then the action that the system should take. So you could say directions please with the same action as before, business or business search, and you just enumerate a few options that you believe users would say. With that, we build an engram, statistical language model, by just counting. We also build an index, an inverted index that we do for search, and that's what we call the training phase. Then at runtime, you speak, the recognizer is using the engram, statistical language model, and it recognizes something like directions. And then the information retrieval engine figures out that based on that index, that's what you have to do. And that's the runtime. And what we do is, after we collected actual speech of people using the system, we use that back to replace that data store with things not that the developer thought that they would say, but the things that they actually said. So after that, the feedback loop is working, and it will behave closer. I mean, it will get better and better accuracy with real users. And that's a not very common way of building voice control systems, but we feel it's much more robust. When you say the right thing, it works about the same. When people speak the way they do with these fluencies and without knowing the menus, it works quite a bit better. When we build the language model, one of the things that we did is we want to build a language model that covers everything with relatively few examples from the developer. So we use a general domain language model that we interpolate with a small language model created with the examples that the developer provided or that eventually the user gave. And that's how we make it more robust. The information retrieval engine, or the IR engine, is what we use traditionally, but if you have a lot of data, you can also learn a classifier, in this case a linear classifier, where the weights are not computed by the TF-IDF formula, but rather you can learn through some machine learning algorithm. In this case, we use maximum entropy. What we've seen is that if you have a lot of data, this does better. If you don't, the TF-IDF style performs better. So this is just a pass of saying we can use techniques that were developed for voice search and use them for voice control and get much more robustness, which we think is very important for gaming scenarios, for places where the user just is not going to say exactly what the system expects. So now let me jump to about leaving gaming and go to automotive. We know that voice interfaces in the automotive are becoming more and more important. You may have heard about ForSync. which is a product that Ford Motor Company deployed 3 years ago, started deploying 3 years ago with one of our product groups. And in particular, I mean, this allows you, it's popular because it only costs $400 and it lets you initiate calls through your Bluetooth phone, any Bluetooth phone, and it sucks all your contacts directly, so you don't need to record voice tags for every one of them. It allows you to play music from your MP3 player or your phone or your iPod, whatever. And it also reads you SMS messages. That's another thing that has nothing to do with voice, like send you an email whenever it's time for you to change the oil. So it's a pretty interesting system. But one of the things that it does is it reads you SMS messages. Since now the text messaging generation is just cannot stay without text messaging, this is a popular feature. And a lot of the car buyers are teenagers and Generation Y customers that just cannot live without text messaging, and they see these features and I got to buy that car. But the system only reads SMS messages because it has a speech synthesizer, but it doesn't let you compose it. All it has is a bunch of canned messages where you can go and scroll and select the response. So the problem with this, there are two issues with this. One of them is constrained. It's only a few. Maybe that's okay. But the bigger problem is if you want to reply and you're driving. We're doing this by voice to avoid you having to look somewhere else. So this is not a very good idea. You want to keep your eyes on the road. So what we did is use the same hammer that I showed you before, but with a different twist. We collected 10,000 SMS messages from some of our interns, and we created a big database there. We used the same trick then. We created a statistical language model, just counting the number of times that unigrams, bigrams, and trigrams happen, and feed that to the recognizer, and created also an index, and again a TF-IDF or IR technique. So when you receive a message that says something like lunch,
no, I can't have lunch today. How about next week?
So maybe that's what the person says. And maybe the recognizer doesn't get it correct. In this case, you'd see that some of the words are incorrect. But the advantage of this is that this system is quite robust. Even though there are mistakes there, it only looks at, given that query, what is the closest actual SMS message that somebody sent. And it shows, not today, next week. You look at it and say, yeah, that sounds good. That's not exactly what I said, but that's what I meant. Go forward. So your options while you're driving is you speak, you see a choice, you like it, click, send. You don't like it, keep driving. Don't crash. Wait until you go at a stoplight. And we did some usability study that people realized that because it's a large but limited number of messages, they cannot say everything they want. But they adapt quickly to the fact that they know that if it is relatively short, they have a very good chance of getting it to work. And people adapt. If it is something that requires a much longer message, just wait until you're not driving. This is an example of how the system works.
2 minutes. Maybe. I'm on the road right now. At 4:30 tomorrow.
Notice that it says tomorrow at 4:30, reversed because of the IR engine. But it's fine, that's what the user meant.
No, I'm on the road.
So let me show you a short video that we put together for TechFest a year ago that shows a bunch of the possible interfaces that you can build with speech when you're driving.
So my name is Ivan Tashev and I'm Principal Architect in Speech Technology Group in Microsoft Research. We're in a driving simulator lab and I'm going to demonstrate Commute UX. Commute UX is a next generation in-car dialogue system which allows you to say anything anytime. This is a dialogue system which employs natural language input and the system still will be able to understand you. Let's see how it works. At the beginning of our trip, let's start with listening to some music. Play track live for the party.
This is the life of the party. We gonna
So this was the classic way to listen to send a speech query, but we don't have to specify track or album or artist. Play Paul Simon. So as you can see, the system didn't need the clarification about the artist. Play The Submarine by the Beatles. And it can even understand not correctly specified names. Let's make some phone calls. My Bluetooth telephone is paired with the system, and the computer knows my address book, so I can ask directly by name. Call Jason Whitehorn.
Calling Jason A. Whitehorn, say yes or no.
Yes.
Jason A. Whitehorn, do you want cell, work or home?
Cell.
Calling Jason A. Whitehorn at cell.
So this was a classic and slightly painful way to interact with the Bluetooth phone, but our system can understand and doesn't need disambiguation if the name is unique. For example, call Konstantin at home.
Calling Konstantin Evangelos Lignos at home.
But there is even more. Frequently the driver needs to respond to some urgent text messages, and it's definitely not safe while you're driving. So we can use our speech input to do the same.
Message from Juan, ETA, say reply, delete, call back, or skip.
Reply. In 10 minutes.
Am I right that you want in 10 minutes? Or a number from the list?
Yes.
Got it. Message sent.
Maybe you notice it, but there is some irregularity in movement of our car, and I'm afraid that we have a flat tire. And because this is a rented car, I even don't know how to open the trunk. So now is the time to open that thick car owner's manual and to try to figure this out. But instead of this, our computer already did this for us. So we can just ask how to open the trunk. And we see the proper page here. But then we need to replace the flat tire. How to replace a flat tire. And we go directly to the page of the owner's manual, which describes how to replace the flat tire. Once we have our flat tire fixed, we can continue our trip and listen to some music. Play Norah Jones.
So we do have a driving simulator that we are playing around with to understand what are the impacts of the interface in the whole driving process. It is complicated. It's not just a grammar. It's not just a dialogue turn. It's like what is the impact on people? And people adjust, and it's important that we put the user as part of the design. So I describe a lot of the things so far on a single turn. But for speech interactions, you need to worry about the whole dialogue. And this is just retaining the context of what the user just said, what the user just did. Let me show you an example of why we think speech for interaction, let's say through the telephone, is much more interesting than DTMF. And you still interact with some of these DTMF systems when you call your favorite business 800 number. I hope this is convincing evidence. Volume, please. Can we raise the volume? Well, unfortunately, I'm not sure.
Oh. Come on, come on.
Let me see if we can do it again.
Sure, Joanne and I went to see Channel with Jerry. With Jerry. Great, great. Probably went to the 84th Street. That's where I always go with Jerry.
Hello, and welcome to Movie Phone. If you know the name of the movie you'd like to see, press 1.
Come on, come on.
Using your touch-tone keypad, please enter the first 3 letters of the movie title now. You've selected Agent Zero. that's correct, press 1.
What?
You've selected Brown-Eyed Girl. If this is correct, press 1. Why don't you just tell me the name of the movie you selected?
Channel?
To find the theater nearest you, please enter your 5-digit zip code now. Why don't you just tell me where you want to see the...
So there is nothing like experimental evidence to convince you that the interfaces should be speech, I hope. So in this case, we have a dialogue, a set of interactions. And in the field, we call this both directed dialogue or user initiative dialogue. And it's who manages the initiative, who's in control. In the directed dialogue systems, the system is in control. That's the most of the systems that you dial today. Something like who you like to contact is a context-free grammar that is simple, that just expects that you're going to say one name of a list, and it will just do the right thing for you. It will guide you through the process. They are simpler to build, and they can work reasonably well as long as users conform with what the system is asking, and that's where the systems tend to break. Users don't know what the menu is, and you get lost easily. This is an example of a system that we built many years ago here.
Good afternoon. Who would you like to contact?
Alex Acero.
Are you looking for...
Alex Acero. Yes.
Okay. Calling the office.
So in this case, we put a list of all the names of Microsoft employees. You call a number and it will transfer. That's relatively simple. But for many other things, that's just not adequate. So what you want is, just like when you call a regular person, the person will say, what can I do for you? And then you can build a system that uses statistical language model. And this is a mock-up system that we built a number of years ago.
Windows Airlines, what can I do for you?
I'm thinking about taking a trip from Denver to Orlando.
Reservations. Got it. From Denver to Orlando. How many tickets do you want?
From Seattle to Los Angeles.
From Seattle to Los Angeles. How many tickets do you want?
I'm thinking 3. Yeah, that's right.
3 tickets from Seattle to Los Angeles. Correct me if I got anything wrong. Otherwise, say that is correct.
Yeah, that sounds about right. Yeah, that's right.
The total cost is $2,100. Goodbye.
So this actually was the test manager in our product group. We told him that we had built one of these systems, and he said, yeah, right, I'm going to break it. And then we showed it to him. Oh, it doesn't always work, but you know, it is much more flexible. And these type of systems are what AT&T worked on many years ago. They call How May I Help You systems. What we did here is try to make it easy for developers that don't know anything about speech to build them. Because before, some of these other systems also handle user initiative dialogue, but they were very complex and difficult to build. You need to be an expert. So what I'm going to show you here is a plugin to Visual Studio that implemented exactly the application that you just saw of Windows Airlines.
The finished application looks like
it fits in the whole screen.
The green components are natural language understanding, or NLU components. For NLU components, the developers need to provide training sentences for CFG grammar and classifier adaptation. Let's take a look at the main menu components. There are 4 recognition branches, 1 for each task. For the reservation branch, we have I want to make a reservation and reservation.
So that's
please.
what I was saying. You give examples for each of the branches.
I need to pick up some friends from the airport. Do you know if the flight is on time? And flight status. Note that the caller does not need to say the exact words as the training sentences to trigger this task. Now, let's check the itinerary dialog, which is used to collect the origin and destination slots. Both origin and destination are cities, and we already have a pre-built city GRXML grammar for them. Developers do not need to write complete grammar. They just need to provide sample sentences or phrases. In this demo, we provide 3 partial sentences: ... origin ... destination ... flight from origin to destination ... flight to destination from origin, where ... are insignificant words. Our tool will build a robust grammar from these samples. So that's it to build the whole application. Just fill the properties and sample sentences.
So the advantage of user initiative dialogues is that if they are implemented correctly, they can result in a shorter call. They can feel more natural, like talking to a person. And it's useful when you have too many choices. But there are also problems which requires expensive expertise. And that's what that tool that I just showed you is trying to alleviate. But it also can lead to user frustration. The system appears human, but the caller cannot understand still, but the caller cannot use full natural language. We are not there yet. It's not like talking to a person yet. This is an example that I got from Masin Rahim at AT&T that shows what can happen when people actually interact with these systems.
AT&T. I am an AT&T automated assistant. You can speak naturally to me. How may I help you?
I need help from a human being. I can't talk to a recording. This sucks. Give me a human being.
Edited.
You can go ahead and speak naturally to me. I can understand your speech and help you get the service that you need. Just briefly tell me how I may help you.
Months ago, I called up and supposed to have gotten a service where I get 7 cents a minute. Well, I haven't got 7 cents a minute yet. They keep charging me 10 cents a minute. I want to talk to a human being and get this cleared up. I don't want to talk to a recording because a recording can't think for itself. I kind of doubt if a human being can because they don't answer no more.
I can help you with that. Are you calling from your home phone?
Yes, I am.
I'm accessing your account. Please hold while I transfer your call.
So designing voice interfaces, in this case for the telephone in the example that I'm going to show you, is much more than just figuring out the grammars and the turns. To do a good job, you really need to think end-to-end about why is the customer calling. This is an example that maybe you've interacted if you call American Airlines, United Airlines, Northwest, all these airlines that are basically trying to do the same thing, and you interact with the systems. So what our subsidiary tell me work on American Airlines, and they say, well, why is the user calling? And so, well, this is the journey of a traveler. Well, first, you're looking for a new trip, then you booked your trip, but you have no ticket, then you get a ticket, you have existing ticket, and it's the day you're flying, existing ticket, but not flying yet, in transit, all the possible options. So it's important that you understand where the caller fits in, because depending on where they fit in, they have different needs, and you should really customize the experience to match that need. So let me show you an example of what happens if you call, say, United Airlines.
Please listen carefully, as our prompter has changed. Thank you for calling United Airlines Reservation Sales. For your convenience, you can also visit our website, united.com.
Well, I'm calling you. I've checked the website before. I'm calling you for a reason. You don't need to refer me. That's what the user is thinking.
Bonus miles on most bookings. United recommends that all customers visit united.com or the Transportation Security Administration's website at TSA.
This is what happens when the marketing folks get involved in the design.
Up-to-date security and carry-on baggage information. Your call may be recorded for coaching and development of our representatives. For flight arrival and departure information, please press 1. For reservations, press 2. If you are calling from a rotary
the user
dial
hasn't
phone,
said a word.
please
It's like
stay on the
45
line,
seconds
and your
already.
call will be answered by a United sales representative.
Thanks for calling the United Airlines Flight Information Line. I've got up-to-the-minute information for all United, Codeshare, United Express, and TED.
Sounds familiar? You've
Let's
probably
get started.
experienced this at some point.
Enter or say the United flight number, or say, I don't know it, and we'll get your info a different way.
Flight 770.
So this is the first time that the
You said
user interacts with the system.
70, correct?
Yes.
Do you want arrival or departure information?
And you get the idea. Let me show you another example that is a little better.
Calling Northwest and KLM. At any time, tell me which option you'd like, choosing from flight status, world perks, new reservation, or existing reservations.
Flight status.
Welcome to Northwest Flight Information. Please tell me a flight number or say, I don't know it.
Flight 360.
Flight 360, is that correct?
Yes.
Would you like arrival or departure information?
Departure.
Departing today, tomorrow,
So better,
or
but still,
yesterday?
you can see
Today.
how long it is. Let me show you what the interaction is with American Airlines the day
Thanks.
you're flying.
Just a moment. That flight makes more than...
Thanks for calling the American Airlines Advantage Gold Desk. Hello, Tony, and welcome.
It recognizes you
I've
through
seen
caller
you're on
ID.
Flight 1234, departing Dallas-Fort Worth at 3:35 p.m. This flight is scheduled to depart on time from Terminal A as in Alpha, Gate 15. To hear that again, say repeat. Now, can I help you with this reservation?
No.
All right. Main menu. For fares and new or existing reservations, please say reservations. Or would you like flight and gate?
Oops. So, did I click this one correctly?
Thank you for calling American Airlines, the only airline with more room throughout coach. We're glad you called. Our records show you on a 2:30 p.m. flight out of Washington Dulles today, but that flight has been delayed 2 hours because of heavy rain in the D.C. area. That means you'll miss your connection in Chicago at 5:05 p.m., but we rebooked you on a 6:50 flight out of Chicago that arrives in San Francisco at 9:23 p.m. Will that work for you?
Sure.
Great. You're on American Flight 47, departing Chicago O'Hare today at 6:50 p.m. Would you like to stay in an aisle seat?
Yes, please.
Okay, hold on a second and I'll check seat availability. Also, we'd like to apologize for any inconvenience this delay has caused. Please be our guest at the Admirals Club while you're at Dulles today. The club is located in Terminal D across from Gate D26. All right, I have you in seat 22D for your flight out of Chicago. And by the way, the weather in San Francisco is currently clear and 62 degrees. Thanks again for flying American Airlines.
So
Have a great flight.
as a user, you're calling the day of your flight. Why are you calling your airline the day of the flight? Well, it turns out that if you analyze the data, most of the time it's because you missed your connection, you had some problem. Well, the answer is, if through caller ID you register, if we have your phone number and you call with that number, we know that's you. We have a record of you. We know that you're flying that day. We know your itinerary. We know that that flight that you just took got late. We know that you missed your connection. The system already knows all that. So why tell you, check unitedairlines.com? Just I know why you're calling. I'm just going to tell you the answer. That's exactly what the user needs. So knowledge of the user and why they are interacting with the system is critically important for a good user experience. It's important to look at dialogues not just in a voice-only way, but also when you're doing a multimodal. And we'll hear from Alex Rudnicki later about interactions with robots using speech. This is an example that Dan Bohosh built that uses both cameras and microphones as a way to control the interaction.
Hi. Thanks for coming to the triage kiosk. I'm in touch with the best doctors in the world. Are you here for your child or yourself?
Yeah, for my child.
So how can I help you?
She's looking at him also.
Diarrhea.
Oh no. Sorry to hear that. Hi there. What's your name?
Mono.
And how old are you?
5.
So, 5 years old, right?
That shows all the computation that the system is doing, tracking the faces, where the faces are looking, how many people are in the scene, what are they doing.
I don't know. I'm sorry. Has your child been vomiting at all?
No.
Okay. So let's see. Has there been a fever?
Slight.
Have you been feeling tired lately?
Yes.
Let's see. How about abdominal pains?
He's not been complaining about.
Has your tummy been hurting?
Yes.
Oh, I'm really sorry. I hope it will feel better soon. Okay. Do you happen to know if your child has been losing weight?
No.
That's okay.
Yeah.
Have you noticed whether your child's food looks funny? Is it black or darker than usual?
It is darker than usual.
Okay. Let's see. Considering everything you told me, I'd like to schedule an appointment with the doctor, just to be sure. However, not to worry, I'm not that concerned at this point. Can you bring your child to see the doctor this Friday at 10 a.m.?
Yes.
Great. Hope you'll feel better. And we'll see you then.
Yeah.
Bye-bye.
Bye. Thank you.
So this shows that it's important to maintain context, not just the audible cues, but also the visual cues. If you have a camera, you know what the user is doing, how many people are in the scene, and that's how humans interact. So let me talk a little bit about error correction. All these systems, I mean, we've heard for many years that say, well, speech recognition, we can't use it yet because it makes mistakes. But it turns out that we found out that in many cases people make more mistakes typing in some of these soft keyboards or in phones. And that's fine, right? So what's different? Well, several things are different. First of all, you blame yourself and your fat thumbs when you do that. You don't blame the system. Second, you know that you made a mistake. And third, you have an easy way to recover. You press the delete key. But in speech recognition, it's a very different interface. It will make mistakes, maybe not as many in some cases, but it will make them for sure. What do you do to correct them? First of all, you blame the system. And second, you don't know what to correct them. So this is an example of interaction where we try to blend the soft keyboard with the speech to make like a predictive keyboard that uses speech as part of the prediction power.
For this demo, I'm using a press and hold to talk interface. I'll press and hold the record button on the side of the device and then speak the phrase which I want to dictate. This is a useful technique for eliminating extraneous noise in certain usage scenarios where noise is expected to be a problem. Effective speech interfaces. Notice that even though I said more than one word, only the first word and its alternates are displayed on the screen. This allows us to use the same interface as the keypad with which the users are already familiar. I can correct any speech recognition errors by scrolling up and down the alternates list or by providing keypad input just as if I was typing with keypad alone. Notice that as I type the keypad input, the alternates are filtered by the keypad constraints. When the correct word is highlighted, I can select it by pressing the center OK button. Only after I do that, the next word and its alternates are highlighted. So using the combination of speech and keypad can allow us to provide a better user experience than each modality on its own.
So there are other places where we've been doing investigations of where to use speech, in which interfaces it makes sense. So one of them, going back to the Kinect Xbox device, is for game shows. We had a demo at TechFest, our internal science fair that we had earlier this year, and it was a Jeopardy type of game. And what we found out is people tried it and they really, really had a lot of fun. especially if you watch on TV. But one problem with this is that at some point the screen will show something like this, and users will just speak whatever they think the correct answer is. But there could be a happy-go-lucky guy and a happy-go-lucky man. They both would be potential good answers for this, but one of them is right and the other one is not. So we need to do work on word-dependent utterance verification. Traditional utterance verification may assign a very similar scores to both sentences because they are almost the same, they just differ by a short word. But that short word makes a big difference. So we did some work on trying to modify our underlying engine to make this scenario successful. We've also looked at using speech in education, in this particular case, to help children read. And in this case, it's like a game. The idea is that the child is playing kind of like a video game, but as part of this, he needs to follow directions that they are written on the screen if he wants to continue in the game. And if he doesn't read the instructions, the game doesn't proceed. So he quickly learns that that's what he needs to do. And, eventually he will play and play more with this and improve his reading abilities. So needs to read, fight the snakes.
The snake.
Got it right? And he fights the snakes. Sometimes
Pull the door. Pull the door.
pull the rope, but he says close the door. Doesn't work. You die.
I said pull the door.
Wrong.
Fight the snake. Pull the rope. Pull the rope.
Would you like to play that game at home?
Sure. Yeah, I love it.
So that's another example where you can use speech for education. You saw in an earlier talk the use of touch interfaces for mathematics. So in this case, Shaoli built a prototype of a system that uses speech for math interfaces. But in this case, it's not to compose typographically the equation, but rather to reason about the equations. Typically, you write an equation when you're writing a paper or a test, and now you explain what is that you're going to do to that equation next. So can we, rather than having you to type it, recognize that and understand it and actually do it for you? So this is what this demo is trying to show. The user is typing down there. And he gets in a pretty print form up there. And it says, take the log of equation 1, and it does it. So it's not just take the input, but understands it and reasons and does the right thing. Or you can speak.
Take the natural log of equation 1. Multiply by x. Raised to the power of 5. X cubed minus 3x equals 2. Move 3x to the right side of equation 1. Add x squared to both sides of equation 2. Factorize the left side. Factorize the right side. Two x plus 3y equal to 1.
He made a recognition mistake, which can be corrected in that case.
X minus 2y equal to 4. Multiply equation 2 by minus 2. Add equation 1 and equation 3. Divide each side of equation 4 by 7.
So we often show this and get requests from students that want to use this tool. It's just a prototype. But in summary, we feel that speech for gaming applications are important, but they require clean audio. There's a lot of work that needs to happen for that. Robust voice control requires flexible grammar, since users don't know what the grammars are and they just don't follow them. They have these fluencies. They use different choice of words. And voice interfaces is really an interdisciplinary field. You need to think about holistically, to use context, and to think about the user and collect real data. Thank you very much. I don't know if we have a couple of minutes for questions, if we have a quick question. Sure.
So I was thinking about the situation where the user may be required to talk, say words that they aren't quite as familiar with, so the pronunciation is not quite what is expected. Did you guys think about that, or have, for example, Rosetta Stone, when you're learning a new language, how would voice recognition work, or if there are any special considerations?
So the question was about what happens if the user is not familiar with the pronunciation. Well, we definitely have looked at that problem, because it is a big problem. And it's a big problem both for the user and for the system. Sometimes we're building a system that recognizes business names, and a lot of those names are foreign names that the system has never seen before. So it's guessing the pronunciation using what we call letter to sound rules. But sometimes those are wrong. So what happens is that if someone has said that before, we need to match a waveform, that is the correct pronunciation, to the text and learn. The system can learn through the feedback loop how to do a better pronunciation model next time. Likewise, if the user doesn't know, well, can click. In some interfaces, you can click on the screen and you can hear the pronunciation. There are some websites, Forbo, for example, that has many people recording words that are kind of unusual, and you may not know how they are pronounced. But yes, those are important things, and especially for language learning application. In the case of the kid learning, you can go and click a particular word, and the system will pronounce that word. Or you can click and pronounce the whole phrase. So if it is something that is edited content, you can do that. One more question?
Hello. So in the game that you showed, you said like if the complete speech needs to be recognized, for example, the last word was guy or man, right? So why didn't you use like individual word recognition and then like do the game instead of like trying to recognize the complete speech? I mean,
can you repeat? I'm not sure I understand. Which game are you talking about?
Sure, in the Jeopardy game.
On the Jeopardy game.
Yeah, Jeopardy game. So you had like, you said if we try to recognize the complete speech, then both of them will like sound similar to the system.
Okay.
So
actually, in that particular case, it's not doing speech recognition. It's just saying, I know what the answer is, the system knows what the answer is, and it's trying to align what you said as a user with that correct answer. It's just trying to find the alignment, and it will compute a score, how well it matches an acoustic score of how well what the user said matches with what the system is expecting. And it's just comparing. So it's not doing really recognition in that case.
Okay.
What happens is that the acoustic score, maybe you have a very good accent, and you will get a very high score for the first 3 words, even though the last one is wrong. So you need to be able to, you may get a better score than someone that says the correct full sentence, but has some accent, for example, gets a lower score. That can definitely happen. So what you need to do is keep that into account, and that's why it's a little bit tricky. Okay, well, thank you very much. And now we're going to have Alex and Nikki. Come on in.
So you can hear me, I assume. Okay, so my name is Alex Rudnicki, and what I'd like to do in this talk is tell you tell you a number of things. First, talk to you a little bit about the dialogue system work that we've been doing over the years, and then in particular talk to you about interaction with robots. Now, one thing you'll notice on this slide is I use the word language as opposed to the word speech, and I think that's actually a really important distinction. In some sense, at least when I think of speech, it's a fairly shallow form of communication. I can say words. The words can just be words. They may not mean anything. And it's really different from using language. When I use language, I'm trying to communicate a meaning to you or to a computer. And really what's interesting about speech and language is the fact that I'm able to communicate meanings to my computer rather than a set of inputs that then need to be interpreted in the context of the particular state. So let's see. Okay. So this is kind of interesting. I just managed to lose a slide. But anyway, so there are a number of areas of application for language-based interfaces. One of the ones I'll talk about is basically search and rescue that involves coordination on a fairly high level between humans and robots. There are other examples of this might be what you would do in maintenance and logistics, where you have systems that have to cooperate again in some complex task with a human being. And finally, a broader area of application, which is one example of which is domestic robots, companions that can help us do one thing or another in the house. So I have to apologize. There is a slide missing. I don't know what happened to it, but we'll just go on. So let me show you some of the, part of this talk is going to be to show you how things have progressed over the years. And the first thing I'd like to show you is a very old application that we did. I guess that'll be about 22 years ago, quite a while. And there are two parts to it. There's a calculator and there's a calendar. I'll just show you a bit of a calculator because it actually fits into some of the other things we've seen today in Alex's talk and in some of the talks in the previous session. So let's see if this works. Computer. 75. 182. 5,921.6. I'm going to try some simple assignment expressions now. Computer. Set I equals 60. Set J equals 4. I times J. Stand by. So there are a couple of things to notice there before we go on. One is the computer here in this case is listening continuously. You don't have to click on things to make it start and make it stop. But you have to have some way of knowing, for the computer to know that it's being addressed. In this case, we're doing it by having an attention word, computer, and then there's another word, standby, that takes it out of the listening mode. Notice also that there can be different ways of saying the same thing. I can say a number like, well, 1,200 or 1,200, although that wasn't quite one of the examples there. And the point was to be able to support different ways of saying the same thing rather than having to sort of verbally key in particular digits. So this is, again, this is a very early system, but it starts to get at the notion that really what a computer should be supporting is the ability to say something that makes sense to the human being rather than follow a particular input scheme. Now, here's a chain of processing for a generic speech system. There's some form of signal processing. There's what we call a decoder, which in some sense goes from takes you from a set of features to a string of words. A parser, they'll try and make sense or attach meaning to those words. A post-parser, which in this case refers to a stage of processing that attempts to decide how confident the system should be in what it has heard from the human. Should it trust this particular input? Followed by a component that actually maintains the conversation, manages the dialogue between the human and the computer. It does this with the help of what I'm labeling here, domain agent. Actually, it can be multiple domain agents that interpret the inputs that the user has produced in the context of the application state. And finally, there's some way of generating an output to the user. It might be language, it might be a display. And in the case of language, it might in fact be synthesized back so that the listener can hear it. So here's a list of core problems that we try to address in spoken language interaction. There's a problem of recognition that I mentioned, which is mapping speech to words. There's the subsequent step of matching those words to concepts. It's not, again, it's not enough just to know that the words are there. You actually have to have some sense of what the underlying meaning was in that particular set of words that were recognized. You need to manage the dialogue, which is to deal with the interaction with the person as some sort of coherent conversation. There is a context, there's a topic. All these things contribute to the system's ability to interpret what the person said and knowing what to do in a particular situation. There's generation, which is the kind of the step back from the concepts. Taking a set of concepts and expressing them in an appropriate string of words that can be spoken back to, for example, can be spoken back to the person. And finally, there is the, again, I want to emphasize the notion of domain reasoning. You can't really have a conversation without having some understanding of what the person is trying to do, what the state of the world is at that particular point in time, and generally have a framework for interpreting what it is that the person is saying. So here is a kind of a second view of a dialogue system architecture. And what I've done here is attach particular components that we've worked on at Carnegie Mellon, from speech recognition to understanding to dialogue management. I won't go into the details of this in this talk, but suffice it to say that in order to be able to do this kind of manage this kind of interaction, there are quite a few pieces of technology that have to be brought together. And here's a, as it were, a historic view of the work that we've done in this field. What's sort of interesting, without going into the detail that's on the slide, what's sort of interesting is that we've progressed from an initial notion that a speech interface is indeed an interface where you, the user, produces a set of events, a set of words, and something happens as a result, to this more general language-based idea where the words that people produced are actually mined for particular meanings, and those meanings, those concepts, are what drive the interaction forward. So at this point, let me show you another system that we built, a little more recent, that shows a couple of things. One is multimodality and the ability to manage multiple applications on a computer at the same time. Calculator. So there's the old calculator. 25 divided by 9 equals. This is showing that you can, in fact, fix things. This seemed important at the time. Clear. And it still is. 97 times 12 equals. Standby. Personal database. Display Rudnicki. Standby. Select calendar. So that should give you an idea of that particular system. One thing I should point out about that is, with the Office Manager, we started to think of the kind of voice interaction that you saw there in the context or in the framework of an event-driven model, which in turn allowed us to combine both the vocal inputs and the inputs in the other modalities from the mouse and from the keyboard into a single framework of interaction. Okay, so at this point, the kind of key ideas that we work with in building dialogue systems include the following. The first is that of a product or agenda-based control. The idea here is that really the best way to represent the interaction in a particular application between a human and the computer is in terms of the tasks that people want to perform. So if you're going to have a dialogue-based control, you really need to start understanding what it is that people are doing with the application and give the system the ability to model those tasks and thereby provide them with a framework within which to understand what particular inputs from the user consist of. And it's also a way of driving mixed initiative dialogue. If the person doesn't quite know what to say, the system can reference where we are in the task and suggest a subsequent move, and essentially move the conversation along just as two collaborators might do, two human collaborators might do. There's also the notion of plan and plan composition. So if the system is representing tasks that the user wants to perform, it has to have some idea of the structure of these tasks. And in particular, plans are a rather good way of representing these. But there also should be this notion of composing new plans within the scope of some application by composing plan components, let's say from a library, and creating new tasks dynamically, and kind of getting away from very rigid types of interaction. There's also the notion of separating domain and discourse processing. And I like to think of this as separating knowledge of the task that's inherent in the application and the conversational skills, if you will, that a system needs to have in order to be able to carry out an interaction with a human. In the very earliest applications, what you would typically do is mix those two things together. So if there was a need for resolving errors in particular contexts, this would become part of the code for that chunk of the application. But really what you want to do is separate these two things out and in some way try and model the way that humans probably do this kind of thing. We have generic skills that allow us to correct things, clarify what's going on in a conversation that typically are independent of the particular topic that we're talking about. And this is the kind of thing you want to have reflected in your dialogue system. Another notion has been that of concept-based dialogue flow. And it's sort of a notion of concept in, concept out. Once you've abstracted out the meaning of what's going on in a particular input, you drive the interaction based on that meaning representation and not on the details of the input. There's obviously a relationship between the two, but it's not the minutiae of the input that drives the conversation. And similarly, well, not similarly, but what flows through the system are conceptual representations of what's going on. Once you need to communicate with the user, then you transform that back into some form that's appropriate to the communication. That might be something the system says, it might be a display, it's whatever appears to be appropriate. And the kind of another view of the third bullet is emphasized in the last one. You do want to separate the task and the domain knowledge that the system possesses. And in particular, you want to be able to do things like recover from errors in ways that are independent of the specific application that's being used. So let me show you another video. This is a more recent system that may or may not exist. There it is.
Hello. Welcome to the Carnegie Mellon Communicator. Are you a registered user?
Hi, this is Alex Rudnicki. I'd like to fly to Charleston on March 15th. The past 30 years have seen a number of breakthroughs in speech recognition technology. We have gone from isolated word to connected speech recognition, from speaker-dependent systems to speaker-independent systems, and from small vocabularies to unlimited vocabulary dictation. An interesting aspect of all these tasks is that they are not representative of the day-to-day interactions that we are used to. Spoken language raises a number of new problems, such as unrehearsed non-grammatical speech, ambiguous, imprecise, or incomplete commands and requests, interruptions and barge-ins, unstated assumptions and undeclared preferences, as well as the use of clarification dialogue. Let us look at an example of the airline reservation task, which illustrates a number of these issues. So the point of those remarks is essentially that although language is a powerful mode of interaction, it's inherently ambiguous. And you need to have systems that can flow with what is going on, make sense of the input, make sense of the interaction, even under these conditions of uncertainty.
Hello. Welcome to the Carnegie Mellon Communicator. Are you a registered user?
Hi, this is Alex Rudnicki. I'd like to fly to Charleston on March 15th.
Can you... Hello, Dr. Rudnicki. I'm glad to hear from you again. You can now ask me for help. A flight on Wednesday, March 15th. You can fly to Charleston in South Carolina or Charleston in West Virginia.
South Carolina, please.
I have a non-stop on U.S. Airways departing Pittsburgh at 11:35 a.m. arriving in Charleston.
How about something in the evening?
Traveling. I have a U.S. Airways flight departing Pittsburgh at 6:41 p.m. arriving into Charlotte at 8:04 p.m.
Notice the recognition isn't quite right, but the correct meaning is extracted.
Okay, I'll take it.
Okay. Will you return to Pittsburgh from Charleston?
Yes, I'd like to come back on Saturday.
Traveling. I have a U.S. Airways flight departing Charleston at 11:05
Do you have something later?
One moment. A later flight departs Charleston at 1:20 p.m. arrives into
Yes, I'll
Pittsburgh
take that one.
Will you be needing hotels or rental cars?
No hotels, no cars.
And so on.
No cars. Do you need a hotel in?
So let's go on from there. What I'd like to talk a bit about now is a domain that we would be working with more recently that has to do with coordination in human-robot teams. So the idea here is you have multiple robots, possibly multiple humans, trying to do something together. And the particular domain here is a treasure hunt. We have a space, it's not necessarily explored, and there are objects in this space that need to be located and, let's say, brought back to a base. Now, in this particular case, what we have is an architecture that includes both language-based interaction, but also a multimodal interface, essentially a map that can be interacted with a pointer, with gesture, and an interface to a robot system that consists of two broad components. One is again, a domain reasoner that tries to manage the knowledge of the system in this particular domain, and what is referred to here as a play dispatcher, which is a component that manages the actual robot actions in the environment. And we'll see an example of that. What's sort of interesting with human-robot dialogue is that it brings together a number of fairly interesting problems. One of which, in the version that we're working with, is multi-participant dialogue. You have more than one robot, you have more than one human. How do the robots know what to do, or who to listen to for that matter, in the appropriate way? So what you need to do is to develop techniques that allow the robot to decide whether it's being addressed, give it ways of managing turn-taking, controlling the floor, and so forth. And these things can't really be managed in a rigid form that you would have in a one-on-one dialogue in the systems that I've shown previously. So for instance, there may be one conversation going on between a human and a robot, but there may be something else that happened that needs to be communicated. So there need to be ways of understanding how to interrupt and so forth. There are practical issues of integrating all these agents into a single communication space. If you have a set of people around a table having a meeting, they can more or less manage their participation. How do you do that when some of your actors are in fact robots? You have to take care of notions of grounding and of shared ontologies. In this kind of task, in fact, in many kinds of domains, the humans and robots need to develop new kinds of information about the environment. So simple things like a new location. That has to be communicated, that has to be understood. Effectively, that concept, if you will, needs to be properly grounded. What is the process by which that can be established? And there have to be ways for humans to be able to share knowledge with the robots. In particular, things like instructing them how to do something. Give them a particular plan that makes sense and have the robot understand that in a way that can be executed in a independent, in a unambiguous fashion. So to summarize those things, there's the problem of grounding. How do humans and robots agree about stuff in the environment? There's instruction, which is how do you allow robots to learn to do something by being instructed by humans. In this particular case, and I think in most cases with robots, there's a need to be able to understand and communicate spatial concepts by language. And finally, there's this problem of multi-participant dialogue management. How do you manage your own participation in a group of other agents, all of whom might be speaking? So let me show you a final video that shows some of the things that we've been doing
Alfie, go home.
with the robots.
Going to home. Bashful,
This is Alfie moving to Bashful listening.
Go forward 2 meters, turn left, then go forward 1 meter.
So this in particular is a situation, is a simulation, but actually replicates the space in which we conduct experiments with the actual robots.
Okay, completed.
Tag this Jupiter.
Okay, this is Jupiter.
Turn right and go forward 4 meters.
So we've established there's a location called Jupiter, and this now becomes something that can be used in subsequent interaction with the robots. Not just that robot, but in fact all of them.
Name this Tango.
Okay, this is Tango.
Go back to Jupiter.
Going to Jupiter.
Decker,
Bashful
go to
here.
Tango.
Moving to
Going to Tango. Decker here.
Notice that
Moving to
the speaker is able to interrupt what the robots are saying. So if you know what's being spoken, you can in fact interrupt and not have to listen to the entire thing.
Start learning zigzag.
Notice also that when you talk to Alfie, it's only Alfie that's responding.
135 degrees.
The other robots know enough that it's not that they're not the object of the interaction.
starting subsequence.
So what we're showing here is a simple form of instruction. The speaker is telling the robot how to put together a particular sequence that's going to be called a zigzag. The robot is listening. It's not actually executing the actions that are being requested.
Sequence done.
Stop learning.
I have learned zigzag.
Alfie, perform zigzag.
And having remembered that and having a tag for it, it can now go and actually do that set of actions. Okay, let's stop that there. All right, so let me recap some of the points that came up. One which is very important is for robots to be able to manage their participation in the conversation. In the other systems that we've seen where there's one computer and one human, that process is actually pretty straightforward. You talk, I talk, you talk, I talk. Here there's a problem of trying to understand what the group is doing and when I can talk, when I can interrupt, and so forth. I'm being told to wrap up, so I will wrap up by running through some of these remaining slides. Another issue that comes up is what the proper architecture should be for these kinds of systems. Should there be a single dialogue system that interfaces the human to multiple robots? Should there be multiple dialogue systems that are self-contained within each robot, or are there sort of hybrid combinations of these that exploit one or another advantage? And again, this is some of the issues that come up. There's, again, the issue of managing knowledge. This is something that is not, doesn't really come up as sharply in older styles of applications as it does in this domain, but it's nevertheless extremely important. How do you manage the knowledge that the robot has? There's also the issue of mapping the elements of what the system knows about tasks in the world to the underlying planning system that the robotic system has. And finally, there's the issue of managing learning. How do you have a process by which you can teach your robot by language to start to do new things? So finally, in conclusion, the neat thing about robots and humans is that it allows us to move the kind of work that we've been doing with spoken language systems into the world, to sort of situate it in environments where a new set of problems they come with their own set of problems. There is a much greater uncertainty about the world. There's the need to learn about the world with the help of humans, and there's a need to develop new kinds of architecture that can support this. So, thank you. If there's any questions, it'd be actually, if we could have a microphone. No questions. Sorry. All right. So please come talk to me afterwards.